Yeah, thanks very much. Warm welcome, everyone. I'd like to thank you for coming to that conference. I'd like to thank all of the organizers for making that possible. And I'd like to thank Jonathan yet again for bumping me up to that showcase slot after one of the talks we actually selected got cancelled because the person didn't come. So I'm very grateful to be able to present what I have to say to all of you. I want to emphasize two things. First of all, it's joint work with Anyway, it's joint work with Tim, and the other thing is it's really work in progress. So I don't often do this, but I really enjoy to talk about something that's current, ongoing research. So we're pretty sure we have something nice, but we're not at all sure whether it's final, and maybe there's one question which will just bump us off, and it'll take another couple of months or so. Okay, anyway, so I want to talk about how to represent consciousness mathematically. And obviously, that was part of what mathematical consciousness science was about from the very beginning. So when we wrote this page of our association, we put it in there. It was a goal, it was a vision. And correspondingly, there are actually a few projects which have to do with that. So you can see, I won't mention the names now, due to brevity, due to time constraint, but a couple of you are working on something which is related to that. If I forgot anyone, I did it last night, so I apologize. In any case, so that's good. But one thing that's not so good is that there's actually a lot of work that has been going into that before we even thought about science, at least I did. And I thought for this conference it's very good to actually talk about that work. And that is specifically the work about quality spaces by Austin Clark, which was mostly which started in 1996. And so I want to start off with talking about these ideas. So that's this idea of a quality space. What is a quality space? It's all from that book. There's another book from 2000 which summarizes the idea. So what I want to do now in the next two slides, I want to tell you how this is defined. That's a reconstruction of what he says in 100 pages. It's complete, so you don't actually have to read the book, other than if you don't understand something. So what I'm saying, it's not so complicated if we take a slightly mathematical perspective. What you're going to get is a constructive definition, which means I'm going to tell you how you build these things. And you're going to get an operational definition, so it's built on the following three things. So that's the set. So we assume we have a single subject fixed, so it's not about speaking about intersubjectivity and so forth, so we just pick a single subject. We pick a class of stimuli to present to that subject, much like what Ariel has in his talk, for example. And what we need is a number of tasks and responses from the subjects in this task after the presentation of the stimuli. So that's abstractly speaking the setting which you need in order to pull through the following definition. Now there's three steps. And the first step is a step where we introduce something called global indiscriminability. And that's basically two things. So first of all, there's a specific task. And the task is to find out whether the experiencing subject, the person in the lab, experiences two stimuli as discriminable or as not discriminable. I'm going to black box how you do that. I'm going to black box the idea of inferring that. That's just a task, and the definition assumes you somehow, maybe not successfully, but in a certain sense, solve that task. And once you have that task, so you have sort of a mathematical object already, the discriminability relation between stimuli, but you introduce a new definition, and that's called global indiscriminability. And we're going to say that two stimuli are globally indiscriminable if and only if they're indiscriminable. So I suppose that's a good thing. And the second, more important requirement is that they have identical indiscriminability relations to all other stimuli. So that means if you have two stimuli which are globally indiscriminable, you cannot discriminate them. If they're globally indiscriminable, they sort of pick out the same experience among the stimuli which you have presented. Sorry, this is actually, yeah, and I should say this, so you do this for conceptual reason, but it's actually making this thing an equivalence relation, so that's very good. So what you do in the next step then is, basically you define something, and what you define is you take the space of stimuli, which is this curly S, and you just mod out the equivalence relation. So that just means you take the set of equivalence classes of the stimuli with respect to the global indiscriminability equivalence relation. That's just something you do technically, mathematically, it's like 40 pages in the book. And what you introduce then, or what you get then, is what I just said. You get something which you can meaningfully call individual experiences in the class of stimuli. It's not 100% ensured that these are sort of individual experiences, but at least you cannot distinguish between them based on the stimuli. And that's what Clark calls qualities or sensory qualities, and that's what everyone else calls qualia. And we're going to denote them by little qi. So that's what you do. That was the first step. So we basically got this one set which we're going to use to build the sort of spaces you've seen, for example, in Ariel's talk. The second thing we need to do is we need to take something into account which is called relative similarity. And again, we have a task and a definition. And the task is, again, find out somehow whether the experience of Q2 is more similar to Q1 than the experience of Q3. So that's why it's called relative similarity. So we have two experiences. Sorry, I'm saying experiences. I should maybe say qualia. I mean elements of the set QC prime. So you have two of these elements, and you have a third, and you can compare two to the third. That's just what you do according to Clark. And when I say task, by the way, I don't mean that's something simple. So that's what Lucia pointed out really nicely. So it might be very, very complicated to actually do that. But we're mathematicians, so we can just generalize over that, and just assume it's done. So what you do then is basically, we're gonna try to find a graph. We don't know whether it exists, so we don't know whether it's unique, but that's just what sort of the procedure is in the book. We're gonna find a graph, the nodes of which are the element QC prime, which we introduced in the beginning, and the edges are posted labeled edges that reproduce this relative similarity relation which we just introduced. So what does it mean? Here's an example. So I just called them all QI because I was too lazy to do this. PowerPoint is really sucks with this formula. My first PowerPoint talk, by the way. I always use LaTeX, but I figured there's so many small images. Anyway, so we got these nodes, which are just elements of the space QC prime. They're called QI. And we draw edges in between of them. And the goal is really, so this pointer doesn't work on the screen, but the goal is really to make sure that any such pair of edges, so it's a coset, which is a partially ordered set, so any such pair of edges should have the same coset relation than the relative similarity we found in the task. So that's what we're trying to find. We don't know whether it exists, and there might be multiple solutions, but we're just assuming we have one. Or Clark is just assuming we have one. Yeah. And so that's the second step. So we got this graph. Yeah?
Is that right to satisfy a triangle inequality?
So let's talk about this later, because I'm going to take it apart anyway, so I'll do the job for you. But in any case, so that's the second step. So basically we have this graph roughly. And the third step is something which is called multidimensional scaling. That's really crucial. You also heard about it in Aaron's talk. So the result of it. So what we're going to do now is we're going to now find an embedding of that graph into a Euclidean metric space, which means just R to the n. And we're going to try and have an embedding which is such that the poset relations of the graph are reproduced by the distances in the space. Okay. So that's the procedure. So why I'm saying this? The original goal of that talk was to tell you, because you might find it interesting and it's good to know, that has changed a bit. So I'm actually telling this as one of the best examples we have that's actually applied with some variations in the lab to construct these spaces. And what we can now do, we can now ask, is that about consciousness at all? Just to address Pete's question again, what the really important point is, this is a reconstruction of what people do. This is not trying to be an improvement. The improvement is coming in. But anyway, so let's look at it and let's ask. So this is one example. We've seen a couple of other examples on the initial slide. So let's ask, so what are the origins of that structure? Obviously, we're all interested in, so the thing we're really interested in is the structure of conscious experience at the very right. Do we have that here? Well, the one thing we know, well, the metric R to the n, basically, well, that was just introduced for mathematical convenience, because a computer it's much easier to code something in Rn than if you have poset label graphs. So that's clear. So that means both the elements of Rn, and namely those which haven't been in the original, or are not, to be precise, in the image of the embedding of the original QC prime, they are just introduced for mathematical convenience. They're not really there in experience. Second thing is, the metric isn't really there. We just introduced it for mathematical convenience. So that's clear, so we haven't got rid of that. What about another source of structures, laboratory operations? So here we could arguably talk about the class of stimuli. I don't find that to be very valuable. And I just wanted to introduce one of these quality spaces. There are others. For example, there's one which was introduced by David Rosenthal. And in these others, you can see nicely how some of the structure come from laboratory operations. Like, for example, the topology in one of these proposals just comes from the topology of the stimulant. You can see that directly. So again, that's not God, that's not necessarily conscious experience. So what about conscious experience? Well, basically here we have two options. So we could talk about the post-it labeled graph, that's still there. Is that like the structure of conscious experience? Or maybe just a relative similarity relation, so what is it? And the point of this whole talk is to say that we don't actually have any idea how to decide that question, because we did not agree or did not come up with a definition of what the structure of consciousness is in the first place. So we don't even know or agree upon what the term mathematical structure of conscious experience means. We have intuitions, these intuitions are good enough for papers, but we can't go beyond these. So just to paraphrase that, we don't know what it means to say that consciousness or phenomenology or the phenomenal character has some mathematical structure. We have ideas, we can talk about them, but that's where it ends. The goal of this talk is actually to make progress. And I had that question on my mind for quite a long time. And I had a few ideas and none of them really made sense to me. So luckily we went on that cabin just in August. So that's cabin, that's one of the participants, it's Polly the sheep. There was just one sheep on that cabin, and because he really liked company, he came over all the time. So when we discussed, he would come over and just, I think he understood part of it because he looked so intense, no kidding. He also tried to eat the whiteboard, I should say, that wasn't so cool. Anyway, but so one day at the cabin, late at night, Tim and I were sitting in chairs, looking at the mountain sky. That's Tim here. And we were discussing that question. And so we had this very simple idea. And that's really the simple idea I'm going to present now. Okay, there's a bit of math, but the idea is really simple. And we had that simple idea, and I think that idea is, or at least for me, that's the first idea I've seen to actually answer that question. And here's the state of the project, which then resulted from that idea. Okay, so I'm going to give you a definition again. This time it's going to be 5 slides, but I'll be nice and careful. And the definition is an answer to the question, what is the mathematical structure of consciousness? But first of all, it's an axiomatic answer, so it doesn't matter what you take consciousness to be or what you take qualia to be, as long as it satisfies these very weak axioms, which you're going to see. And then it's a definition in the sense of the term mathematical structure of consciousness. It is not an answer what the structure is. We'll speak about that at the very end. Okay. So, first of all, this is really simple. First of all, we're just going to introduce a name. So, a few symbols. So, little e is a conscious experience. Big E is a set of experiences. We're just ignoring problems with set theory for now. And so, everything I write in yellow is an intuition, which is not at all central for the axiomatics, but explains it a bit. So, the one thing we want to do, we want to introduce a set for every conscious experience. We're going to call it A of E. That's the set of qualia of such an experience. And it doesn't matter what you mean. It doesn't matter what you think. The only thing that matters for us is that if two experiences agree, then also there's sets of qualia. First step. Second step now relates to Vanya's talk in the boot camp. So Vanya had these nice definitions of qualia, and what we had in mind made sense in the only one of them which made sense, so that's a good thing. And that's the axiom, it's an axiom, which means that's something we now choose, and that's the axiom is, morally speaking, the idea that qualia constitute conscious experience. So it's just the opposite error than what we should see. So the idea is we're now going to say if the sets of qualia are the same, then the experiences are all the same. So I'm going to introduce an abbreviation for that. So I'm going to call it, so it's qualia constitute experiences, so QCE. Yeah. For the physicists among you, it should be natural QCD, so it's just QCE. So that's an axiom we're going to put in, and that's just going to matter for what follows. Okay. And so we're going to introduce another symbol, curly A. It's just all aspects of all experiences in the set E. And because of this axiom QCE, we can actually, so that there's an equivalence in these axiomatic systems between conscious experiences and sets of qualia. And so what you can do is you can, instead of talking about experience, you can talk about a subset, or I prefer the characteristic function. So this is basically, this means the following. So if I have a conscious experience, then there's a particular choice of qualia, or we call them aspects of conscious experience, which is unique or equivalent to that experience, and that are just the green bars. So this is the picture of a characteristic function you see over the set. I choose it discretely just because PowerPoint is really difficult to play around with. Yeah, so I hope that part is clear. Subset or characteristic function. Okay, second ingredient, in order to pull through the definition, is variations. So a variation, you could say it's something that changes an experience E into a different experience E prime, but I don't actually want to talk about something, so variations are just changes of experience. And because of this axiom again, QCE, they are changes of the function, of the characteristic function of an experience. So you could also say they are changes of the subsets of qualia. And we're going to introduce an axiom for that. So, and I want to explain that axiom based on that figure. So if you look at the very bottom, so you have one experience, that's the green aspect, the green qualia, and then you have a variation that changes these aspects. So far, so much we have already. But what we don't have just by introducing variations is, we know one subset gets mapped to another subset, but we don't know how the individual elements get mapped. And so that's what this axiom introduces. So we're going to say for some aspects, not all of them, of a conscious experience E, that means for some qualia, it's clear which variations change that aspect. And for them then, we're going to assume that the variation is actually a mapping on the space. So it takes elements of the aspects and gives new elements, new aspects. So it takes qualia and gives new qualia. So that's a technical assumption. Why do we need that? Because otherwise, it's not even well defined whether and how a variation changes aspects of conscious experience, which is just our word for how a variation changes qualia. So that's what we need. Okay, and that's it. So we don't need anything else. We have introduced this little bit of formalism. Now we can actually say two more things. And here's the first part, and then there's another thing, and then we're done with the talk. The first part is, it defines what the phenomenal character of a relation is. So we're going to call it an R aspect. So there are two conditions. So an aspect, which means a qualia, is the phenomenal character of a relation if and only if, first, there is a variation of that aspect which leaves the relata of that relation invariant. The relata are also aspects. And second, every variation of the relata do not leave invariant the relation. Okay, that's a bit dense. Let's unpack it. Here's the night sky, which Tim and I looked at when we had that thought. And here are 3 stars. And I'd say that for most of you, these 3 stars now exhibit a relation which we could call triangleness. And so now let's just see how this works with the definition. Well, first part of the definition, there's a variation of the relation, which leaves that's the triangleness, which leaves the relata, those are the stars invariant. Well, okay, that's something we can do. So for example, we can push this star down here, which means the stars are still there, the conscious experience of the individual stars are still there, but the conscious experience of the relation changed. It's not there anymore. It's a different relation. It's a line now. Something like no triangles. So the first condition is satisfied. The second condition is the variations of the relata do not leave the relation invariant. So let's look at the variation of a relata. Well, the simplest one is we take it away, so it's gone now, and therefore also the triangleness is gone. So those are just these 2 definitions. And so now we know what the phenomenal character of a relation is, and now we just have to put the pieces together, and that's the last definition. So now we're going to say that the mathematical structure so a mathematical structure in general, just for the experts, I mean something like a structure in the sense of heterogeneous algebraic structures in universal algebra, which just means like fields, vector spaces, rings, the typical thing you have in mind, manifolds even, everything fits there. So a mathematical structure is a mathematical structure of conscious experience if and only if 2 things hold. So first of all, it needs to be a relation on some set. And that's almost always the case. When you have a function is a relation on the product of source and target. So you can basically almost forget the first definition. The second condition is much more important. The second condition basically just says, and now you need to have one phenomenal character of a relation which holds for all of the elements of the relation. So we have a relation on this set here, and now what we're going to do is we're going to take an element of the relation, which is just a tuple, one thing from every space, from every set, and now we're going to want that there is one phenomenal character of a relation which is, yeah, that's it. There's one which holds true for all of them. Okay, just trying to be a bit clear. Okay, that's it. And I know that was a bit dense, but the point is this answers the question. So this defines what the mathematical structure of conscious experience is. And so far we think it's a good definition, but that's of course up to you guys. I know it was a bit dense, I shouldn't have taken this time here to try to sorry about that. Anyway, okay. So let's summarize a little bit. What are the crucial ingredients in the definition? First of all relevant mathematical structures are essentially just relations. That's really, really important because you can only make sense of relations in experience. Second of all, relations are qualia. Yeah? So not only the relata, but the relations themselves are in experience. Third, you can remove the relation without removing the relata, but you cannot remove the relata without also removing the relation. Okay, general picture. Which structure is there? Well, the point here is, this is just a definition of what the term refers to. And now we have to find out what is the structure. We've heard, there was Camillo's talk, which had an answer. There was Ariel's talks, which had certain thoughts. And the point is that's what you have to do, and you have to do it by various means. You can use introspection, you can use laboratory operations, like in quality space. And these are the existing research projects. And so what we hope to do is really provide a foundation or a target for these existing projects against which to see whether they're really on track. And just to emphasize, because from here on, what we need is you guys and your guys' experience. By the way, guys is gendered. Or in my language, just to emphasize. But anyway, so that's what we need, and yeah, okay, good. And I want to squeeze in this one slide for those who are in here and thinking, okay, so why should we even represent consciousness mathematically? And why does this guy talk about this? I mean, obviously, like, because he thinks it's good, but is there any other reason? Well, there's some obvious reason, like, for example, colloquial languages won't do. That's why we replaced these text-based computer games with other computer games in the 90s or so. I don't even know that. So that's one thing. So we need some other tools to represent the richness of consciousness. Then, of course, also non-trivial brain models are mathematical anyway, so if you want to patch that to consciousness, you're already in the ballpark of math. But there's actually a much more important reason. And the much more important reason that, in my mind, this and the whole thing, I mean also what you guys are doing on that, is potentially a whole new way of doing consciousness science. It's potentially a key to understanding the problem landscape rigorously. And what I mean things like, what is subjectivity, what is personal, what is private, basically the whole ballpark of philosophical questions. Potentially we can have a different and potentially more helpful angle. We can actually solve these problems. We've done, so I mean we can talk about, there's another talk, but that's actually done already for at least one of them. They can be constrained in cornerstones for various theories of consciousness, like Julia, for example. They have a space, many other theories don't. So if you want to have a space and you kind of know which one you have, that could be like a rigorous constraint, like making your landscape smaller. And if you're not convinced, then really think about, someone could have asked, like in 1940, why should we represent information mathematically? And there were maybe a few good reasons, but there weren't so many, which is the reason why Claude Shannon let his papers sit in the basement for 4 years before publishing it, yeah? Because it wasn't so urgent, yeah? And that's the point, and see what it did, and I think that's the same here. And, you know, we talked about this in the boot camp, and Ian was like making this comment, yeah, I think it's gonna be very long, but here he is. And so my point is...
That's a terrible picture of
me. Yeah, I took that, it was intentional. You got stuck on that frame, and I was quick with it. Anyway, but the point is really, I don't think it's far away anyway. I think what we really need to do is we really need to sort of work together, combine our expertises, and I think that if we do that, you know, we talk to each other, we work as a group, I think something potentially really nice is at the horizon, and for me, really nice means groundbreaking. I'm German, I'm ultra-skeptical usually. So yeah, that's it. So that's my talk, that's what I wanted to say. Thanks for the attention, and yeah, please talk to me.